your comment and forwarded your voicemail.
हाँ दिव्या, ये कहाँ से उठाया डाटा?
ये वो मैं वही आई हूँ है वो कह रहे कि उन्होंने कोई तो नहीं याद है इन्होंने देख करके डाल दिया है।
ये तो 12,434 सैंपल दिखा रहा है टोटल L2 में। ये पता नहीं कहाँ से सैंपल उठा लिए इन्होंने।
तो अब कर रिसेट कर लो ना, दे दो। अरे आप मुझे दिखाओ ना, आपने क्या मैसेज किया था? और बुरे ठीक है आप भी कर देना है अपनी खाली फॉर्मेट भेज है नहीं यहाँ पे आ रहा है ना, इससे कंफ्यूजन हो रही है कि दिस फॉर्मेट है, वहाँ पे आके मैसेज करना है बस अपडेट कर दो।
नहीं, ये जो आपने लिखे हैं ना इसमें सैंपल टेस्टेड इतने हैं, इसमें लिखा हुआ है
डिटेल्स है ना वो, ये वो पता नहीं कब ये 5 डेज का दिखा रहे हैं।
अच्छा, तो मैं तो आपको रेमेडियल मेजर दे दूं ना बस।
रेमेडियल मेजर
So very good afternoon to all. I hope Dr. Al Vijay Anand has joined and he has checked the screen also. Okay.
Yes.
Just we are waiting. Once again, good afternoon to all. Welcome. Just I'm waiting for our advisor sir to join. He's in the meeting hall. Just I'm checking his presence and I shall let you know.
Okay.
Thank you very much.
So am I audible properly?
Yes, sir, you are audible.
Okay.
You are audible.
Yeah, thank you.
ठीक है मैडम, ऑल द बेस्ट। ओके, आई विल ट्राई करना है।
अच्छा काम किया। तो फिर इनको किसी न किसी लिख के पर इनकी कमांड ज्यादा ही पूरा पैसा नहीं दे पाएगा तो ये टेकिंग 70
Sir, good afternoon to all. Our advisor sir has joined, and now we can start the session. A warm welcome from Shyama Prasad Mukherjee, National Institute of Water and Sanitation. Perhaps you know that this is a premier institution established by Government of India under Jal Shakti Ministry, and this is a very new institution, but we are trying to elevate the status of this institution to the international level. And during last 2 months, we have been conducting webinars to disseminate knowledge amongst all the stakeholders across the country. And today, we are having a very important and very interesting topic. And we have invited Dr. L. Vijay Anand from IIT Ropar to give his presentation. Dr. L. Vijay Anand has been associated with Indian Institute of Technology, Ropar, as an assistant professor of civil engineering for the past 7 years. He obtained his MS and PhD from Howard University, USA. In his MS research, the effect of biochar that results from stubborn burning was explored. In his PhD, the problem of uranium contamination of soil and groundwater was explored using natural and synthetic geomedia. Further, in his postdoctoral research at Oak Ridge National Laboratory, US, he worked on the Van zone transport of uranium, addressing problems related to uranium legacy waste from Hanford site. Currently, he is a team lead of Advanced Water Quality Lab at IIT Ropar, wherein his group primarily focuses on the pressing problem related to water and soil contamination, especially in the north and northwestern region of India. In today's webinar, Dr. L. Vijay Anand will speak on the topic, understanding the groundwater contamination of geogenic origins using geochemical modeling tools, underpinning mechanisms and scenario predictions. The groundwater contamination in many states of northern India arises due to multiple factors, one of the primary reasons being its geogenic origin. Comprehensions of this large-scale contamination require an understanding of soil-water interfacial processes that could be aided by geochemical modeling tools. Where the traditional approach of capturing the soil-water interaction using isotherms are limited in scope. The geochemical models capture the chemical reactions involved in contaminant metabolism processes. In this talk, the speaker will focus on limitation of traditional approaches in understanding the groundwater contamination issues. Number 2, advantages of using geochemical models to underpin the fundamental mechanisms of contamination scenario. And number 3, common experimental artifacts that limit our understanding of groundwater contamination. We shall hold this session in 2 parts. In first, almost 1 hour, the presenter, Dr. L. Vijay Anand, will give the presentation on the very important issue, very interesting too. And it is expected that no participants should interfere his deliberation, because after his session is over, we shall keep the session open for interaction. You can question Dr. Anand, and you can comment on this topic also. So with these few words, I request our advisors to speak a few words in this matter. Dr. Isfaq sir.
So good afternoon. First of all, let me extend my heartiest welcome and thanks to Dr. L. Vijay Anand. I have an opportunity to meet him in person also. He's a very learned man and doing very good work in this sector and very committed to the sector. So sometimes we feel that people like him are an asset to the society. So Dr. Vijayanand has done a lot of work under the subject, and the topic in which he wants to talk is very, very important, because right now, due to various reasons, maybe climate change, maybe our pollution and other geogenic reasons, we are facing water quality issues. And now there are many upcoming parameters which we are not monitoring, but now we are facing those issues also. So today's lecture is very, very important, because Dr. Vijayanand will be giving us insight into the what are the origins, especially geogenic origins for the water quality contaminants which normally we are finding in the system, and what kind of work they are doing. So I know people who have joined are mostly practicing engineers or practicing chemists, and Dr. Vijayanand's work is most of research oriented. But this is a perfect chance where the practitioners and the researchers are one at the same platform, and they have an opportunity to share ideas, thoughts, and see questions. So this is a rare opportunity for all of us. That's why I have also taken time to attend this webinar, and I request all the participants to listen very carefully the thoughts of Dr. Anand. And I think by the end of the session, all will be enriched with good knowledge. And then, of course, we will have some opportunities to ask questions to Dr. Anand also and to get clarification. And once again, I extend my thanks to Dr. Vijayan and we welcome him. And now I request Mr. Sekia to take the session forward. Thank you.
Thank you, Advisor sir. Now I request Dr. Anand sir to give his presentation, please.
Yeah, thank you. Am I audible well?
Yes, sir, you are audible.
Yeah, fine, okay. So first of all, yeah, thanks to Dr. Mukherjee and Mr. Ishfaqji. I think it was a very nice introduction given by the organizers of this. And I'm glad to be part of this initiative. As Ishfaqji rightly mentioned, this particular platform gives an opportunity for the researchers to connect with the practitioners. And likewise, I have actually made my presentation accordingly. I think try to limit the equations. I cannot avoid the equations, but I can limit it to the maximum. I tried my best. So the mathematical equations to the minimum. So so with this nice introduction, I welcome you all, and with a very good afternoon, or almost I think a very good evening actually. So I hope the next 1 hour or so will be useful to everyone. So on one request from your side, I think please keep your audio on mute unless otherwise you have any queries, and feel free to intervene if you have any queries amidst my presentation. I would like to take it as a more of a discussion sort of, rather than, although the introducers mentioned that we finish the presentation and go for discussion. Yeah, if you want to reserve your questions, fine, but I don't hold to the questions. I don't like to hold to the questions in any presentation. So feel free to intervene as and when you have a doubt or clarification, and I'll be glad to clarify and move on. So with that note, so I would like to start the presentation. Actually, the title is very straightforward. I think we are talking about groundwater contamination here, that too of geological origins, right? And then it is one of the major sources of groundwater contamination, particular to India, if not the world, right? And then we, especially if you talk about the northwestern regions, where primarily my research is focused on, we have issues like of uranium contamination or arsenic contamination, fluoride contamination, primarily occurring due to geological reasons, right? The mineral media essentially contains these contaminants, and as infiltration happens, these contaminants leach out to the groundwater. And the Water Supply Board or Pollution Control Board, the statutory organizations that are involved in looking at the contamination, essentially go to the sampling sites, right? The piezometers or whatever they have installed, they collect samples and get an idea of what is the contamination, right? And then, but we never track on what caused the contamination, right? So the focus is not on that. And How long the contamination would continue? That's one of the important questions that requires an answer, essentially to know the solution to the problem, right? And then so there are very many scenarios that can happen in the geological strata that can lead to either enhanced contamination at certain times or reduction in contamination at certain times. So how do we ascertain those? So that's where the geochemical modeling tools are going to help us. Okay, so we will look into, so let me move on to my overview or the background info. So as I already mentioned, we are talking about groundwater pollution, but groundwater pollution is essentially mapped, right? So all the water supply board people or pollution control board personnel, that's one of the main tasks, is to go to the field, sample the groundwater, and essentially map the contaminants, right? And then essentially about the origins, we pretty much not have really that much of a clue, right? So what essentially causes the changes in water quality? Let's say, for example, uranium, right? What causes the changes in uranium concentration at various time points, right? So on a temporal scenario. So those are very essential questions, and also spatial scenarios as well. So those are to be addressed to have a solution to these problems. So as already mentioned, as I've already mentioned, we are focusing here on the geogenic contamination and not the anthropogenic reasons that are leading to groundwater contamination. So that it's a separate chapter or separate topic. So primarily in this talk, I will be focusing on geochemical modeling tools, how we have applied in our previous studies, focusing on the uranium contamination. In the Indian context, we have uranium contamination occurring primarily in the state of Punjab, focused in the southwest. Sorry about that. Yeah. Primarily occurring in the southwest region, that's called Malwa region of Punjab, and also in many other states as well. I think going by the CGWB report, there are 18 states in India that have uranium contamination. That's above the maximum contaminant level set by the WHO limits or even AERB limits. So, and we will primarily focus on an effect that is called as soil to solution ratio. I have captured it as abbreviated as SSR effect. Okay, so what is that? We will discuss in this presentation. And followed by that study, I would like to take your attention to another project that I worked on that is essentially related to fluoride contamination. And the fluoride essentially resonates with Rajasthan, right? The arid and semi-arid regions of India. And one of the projects that we worked on, essentially, we looked at the fluoride contamination in some pockets of Rajasthan and what is essentially causing it. So both the uranium and fluoride contamination has the geogenic origins. So essentially, that is what we are going to look at. And finally, I'll give a take-home message or essentially one-point summary that essentially that trickles down out of these studies. Okay, moving on. I think if you look at essentially to understand the contamination, say water contamination, one need to understand it is not a standalone scenario. One need to understand what is happening. So by contamination here, I'm talking about geogenic contamination only, just to clarify. So in a geogenic contamination scenario, one need to understand not just the water contaminant or levels of contamination in water. One need to understand the interaction between the soil and the water, right? So on what causes essentially the levels of the contamination that we observe in the groundwater, right? So be it uranium or fluoride. So if you look at the various processes in the subsurface that lead to the prevalence of contaminant in the groundwater, the multitude of factors that would drive the contamination to groundwater are essentially I'm showcasing here. So one of that is essentially called as aqueous complexation, right? In the sense, let's say I have an uranium that is essentially present in a mineral form in the soil, and as the rainwater percolates, essentially it's going to derive the uranium, right, or release the uranium from the soil to the water that is essentially percolating towards the subsurface or towards the groundwater table. And as the contaminant leaches or the uranium leaches, if at all we have some constituents like carbonate or phosphate that is present in the groundwater system or in the subsurface, just like any other solute, tons of carbonates can be there. If at all it's a calcium carbonate type terrain, I think subsurface essentially. So that can essentially complex with uranium and form uranium carbonate, or phosphate can form uranium phosphate. So we are not really talking about uranium contamination. We are talking about uranium that is combined with carbonate and what it is going to do, and when it reaches the water table, and the form of that essentially is what is going to be of concern rather than uranium alone, right? So if uranium and carbonate complexes, say it's an aqueous complex, and whether it's going to attach to the soil or whether it's going to get released, that is essentially what we are going to, what we're interested in to understand the problem. So there are a number of things that can essentially form aqueous complexes, both in case of uranium and fluoride. We will get into those when we talk about the specific studies. And if at all the particular contaminant is redox sensitive, essentially in the case of uranium, it's a redox sensitive. Uranium can exist in +4 valence state and +6 valence state in the natural environment. And in the reduced state of +4, it forms a, it's relatively less soluble essentially. So it is essentially precipitates out, forming uraninite. So essentially, whenever the uranium contamination is there in groundwater, most likely it is going to be in +6 form, right? And then so the essentially oxidized form of uranium is what is present. But nevertheless, if there is any biodegradation that is happening, biological activities are present, there is a chance of uranium precipitating out of the groundwater in uraninite or uranium +4 form as well, leading to immobilization of uranium. So depending on the type of contaminant, its chemical properties, you may have a redox type reaction also that would essentially affect its transport of contamination, or the levels of uranium or fluoride or contaminant that we see is essentially depend on redox reactions, oxidation reduction reactions. And as I already mentioned, biological reactions can also play a role. If typically organic contaminants are bioavailable, right? So microorganisms need energy or food for the survival, and being organic, it essentially thrives on organic contamination. And even for that matter, if we have iron and uranium present, even in inorganic systems, the biology plays a vital role, right? And then iron can couple with uranium. When iron can get reduced, uranium can get oxidized. Need not be a biological reaction. It may be an inorganic reaction as well, right? And then need not be mediated with microorganisms. So that is also possible as long as the contaminant is redox sensitive. And one other reaction that can happen in subsurface is precipitation and dissolution. I already mentioned about uranium exists in 2 valence states, +4 and +6. +4 being the least soluble. Essentially, the solubility limiting solid is uraninite. So it is around 10⁻⁻⁶ or less than that. It's micrograms of uranium will be soluble at that low level. Micromoles of concentration of uranium will be soluble if it is existing +4 form in the reduced state. So essentially, if it precipitates, it's not going to be mobile, right? Because it's going to get immobilized. So things that are going to dissolve or things that are going to be soluble more or tend to be transported more, and it's going to cause large-scale contamination. Finally, I want to move on to this one of the important aspects which the current presentation is going to focus on is surface complexation, which we simply call sorption or desorption. Sorption is nothing but when the solute gets absorbed onto the surface of a mineral, right? And we are talking about geomedia or soil or sediments. So that is called sorption. Sorption essentially immobilizes the contaminant, and the opposite of that is desorption, right? So whatever attached to the solute, uranium or fluoride attached to the soil, if it gets released, that is called as desorption. So a desorption essentially leads to, essentially if groundwater is getting transported, desorption is going to release the contaminant, and it's going to get transported to large scale scenarios, right? So more the sorption, more it is immobilized. So all these reactions that we discussed about aqueous complexation, redox, biological reactions or bioavailability, precipitation, dissolution, and sorption, desorption, the most dominant that we are looking at, or it's called as surface complexation also. So all these are going to affect the transport, right? Finally, we're interested to essentially look at whether the contaminant is going to remain in a particular place or it's going to travel, at what rate it's going to travel, right? And to predict it and to put some mechanism in place to address the contamination scenario. Right, so primarily we'll focus on the saturated transport, that is essentially groundwater transport. Vertical transport also can happen, that's in unsat region. We will not discuss much about that in this presentation. So with that background, so we move on to how do we really understand the absorption characteristic. As I already mentioned in the previous slide, we are going to look at sorption primarily. It's one of the most important reactions that can happen in the subsurface. And one need to understand how the soil is going to interact with in the presence of water, so that during infiltration process, the minerals that are present in the soil which contains the contaminant will leach out the contaminant or release the contaminant and essentially reaches the groundwater table and gets transported and go to a large scale contamination type scenario. So in the lab, how do we do that is to understand the sorption process is something called as a batch sorption equilibrium studies. These are kind of 1 or 2 day study typically, where we take certain amount of soil, say X grams of soil, and certain amount of solute, Y milligrams per liter of solute, say uranium, certain content, say 1 milligram per liter of uranium, and we mix these to the system, soil and water system, and after certain equilibrium time, we should essentially perform a kinetic study to understand the equilibrium time. So let's say 48 hours, typically the equilibrium time is. Then we essentially separate the phase out. The soil will settle during centrifugation, and we remove the supernatant and check the amount of contaminant, in this case uranium, how much uranium present in the liquid phase. Of course, that is going to be less than Y. You have started with 1 mg per liter, say 30% of this is absorbed, right? And then 0.3 milligrams per liter is absorbed, and 0.7 milligrams per liter should be in the aqueous phase. So that ratio between soil and the water aqueous phase is essentially, we capture it through something called as distribution coefficient. So this is a typical sorption equilibrium study that we perform in the lab. And whatever is in the aqueous phase is representative of the groundwater contamination scenario, right? Your soil has certain capability of releasing or absorbing the contaminant. And the ratio between soil and water is essentially decided by the chemical reactions between them, and it is an equilibrium process, right? And then there is a certain ratio that is being maintained. So we are, as an environmental engineer, I think we are interested in to find this ratio, and that will tell us how much of the release is essentially happening, and what is the contamination one can expect, how long it would happen as we remove the supernatant, how much release is happening over time. One can do it as a continuous study as well. Okay, so that is essentially, and simply put, any sampling at any point of time in the field, if you're tracking the water quality data for uranium, for example, the concentration that we get, essentially we take it as an equilibrium concentration that is in at equilibrium with the soil that is present in the subsurface, right? It is not just the aqueous phase that contains the contaminant. The soil is essentially the source that essentially releases the contaminant. So that has to be kept in mind. Okay, so moving on, I think, so these are the various isotherms, the relationship that I just spoke about. C is essentially the aqueous phase concentration that we withdraw in the supernatant, and how much of that remains in the solid that we capture on a per gram basis of soil. That is called as S, marked as S. The KD is called as distribution coefficient, essentially the slope of this particular relationship that we derived from these experiments. Okay, so if the slope is linear, we call it as partitioning. It's a partitioning process, but many times it is not linear. As the concentration changes, you have a nonlinear type scenario as well. That is called Freundlich isotherm. And if at all the nonlinearity plateaus out, right, beyond certain point, you have a saturation scenario. That essentially is captured by an isotherm called as Lang-Yu type isotherm, and there are many other isotherms as well. But traditional approaches, we go by these either we go for a partitioning or distribution coefficient based, KD based approach, or we go for a Freundlich type. Typically, uranium follows a Freundlich type isotherm, and the last one is the Langmuir isotherm that we see in some cases as well. Okay, so but these are the traditional approaches. As you can see, the limitation of this is very obvious. So we are actually deriving this relationship at one particular chemical condition, at one particular temperature. Essentially, these are called isotherm. Of course, the temperature is fixed, but in the ground, is the chemistry going to be constant? Not at all, right? And then if there is an infiltration, there is going to be dilution scenarios where the chemistry is going to be obviously changing, right? Things that are going to leach into the groundwater. Maybe if it is a carbonate domain, more of carbonates will also leach along with uranium, isn't it? I think phosphates, things that can influence the contaminant can leach out into the groundwater, right? And it can affect the concentration of the particular contaminant of interest. So this particular relationship that we develop at a particular point of space and time is not going to be applicable at a different space and time point, right? So essentially, one cannot do n number of isotherms as well. So how do we solve this problem? Essentially, so that is where the geochemical modeling comes into play, right? And then we have to capture the chemistry that is essentially changing over time in temporal scales and also in spatial scales to look at how the isotherm is going to change when the chemistry changes. So that is what this geochemical modeling tool is going to help us with. And this primarily these days we have moved on from the traditional approaches to the geochemical modeling approaches, wherein the chemistry of the system is being captured, and one essentially have to come up with the influencing reaction set that would of interest to the particular contaminant. For example, in the case of uranium, I mentioned about carbonate, phosphate can influence. So one need to get into the chemistry of the particular target contaminant and should know what are all the other parameters, other chemical constituents that would affect the form of the contaminant or its absorption capacity, absorption potential, or its aqueous complexation potential. So that has to be brought into the geochemical models to have a realistic isotherm scenario, right? So because that is going to tell us how long the contamination is going to exist and also what form the contaminant is going to be, right? The form of contaminant is also of interest. As I already mentioned, uranium can complex with carbonate and form uranium carbonate. We cannot assume uranium exists in metallic state, right? So, and also as it changes, as the speciation changes, its reactivity will change, its absorption potential will change, and it essentially the way to remove or remediate the particular contaminant would also change necessarily, right? So these are essentially the initial steps where we have been using the traditional approaches, but as I already mentioned, kind of people have moved on. I think the research domain has moved on to the geochemical models and knowing these are the lacuna in the traditional approaches. Moving on, I think. So as I already mentioned in the previous slide, you have got something called as KD, right? Distribution coefficient. And we are interested in the transport processes. I think the way we model the transport process is through CDE or the advection dispersion equation that's mentioned here. R is the retardation factor, and C is the concentration of the contaminant, which will vary with time, and D is the diffusion parameter. And of course, you're looking at the concentration, the second order changing with space as well. And V is the advection, the velocity of the groundwater will move the contaminant for large distances. So these are the various processes that essentially would affect the transport of contaminant, which essentially we are interested in, right? So where the KD is, the distribution coefficient is tied to the factor called as retardation coefficient, wherein rho b is the bulk density of the soil and theta is the volumetric water content. Okay, so retardation factor essentially is tied to the KD that we obtain from the absorption isotherm. More the retardation essentially implies the distribution coefficient is high, right? And of course, this we already looked at. The slope of the isotherm is over C. Okay. So moving on, I think this is the equation we solve. Of course, the reaction part is missing in this equation, but anyways, we essentially solve advection dispersion and the reaction component as well, which is the geochemical part. This is the traditional way to solve, and geochemical part essentially if you have to include the reaction component as well to this equation. So let me move on to the first of the studies I would like to highlight, as I mentioned in the introductory slide, the effect of soil solution ratio. This is the uranium study. This is a theoretical work that we have done. I think during my PhD, I think this is the work done using a geochemical software tool called as Mintech. So what we look at here is, let's say you have a contamination of uranium that is present in water, and uranium is known to absorb onto iron oxides in the soil. So if iron oxides is present in the soil, it is more likely it imbibes to oxides of iron and oxides of manganese and those metallic parts, metals that are present in the sediments primarily. So essentially the iron oxides. So since iron oxides are the dominant uranium absorbing phase in the soil, so we are looking at how the iron oxides are going to absorb when just uranium is going to present, right? As I already mentioned, in batch systems, we take X amount of soil and Y concentration of uranium, right? So here what we're doing is we can perform the batch experiment at multiple solid to solution ratios, right? And this, I can take 1 gram of soil and essentially put that in 20 ml of water and do the experiment, or I can give 2 grams of soil given 40 ml, right? So I can just scale it up. So when I do the scaling up of the amount of soil and maintain the ratio, as you can see, my isotherm doesn't change, right? Which is very obvious. That is what we expect. We cannot take tons of soil and get it essentially give gallons of solute concentration in gallons of water and do the experiment. That is not practical, right? But this is what we expect out of just by intuition when the solid to solution changes. Never, regardless of I do with 1 gram soil and 20 ml of solution, or 2 grams of soil and 40 ml of solution, I would expect the same isotherm. And obviously, I could see that when I have the solid solution ratio 3.33 going to say 333 grams per liter, my isotherm is same. The relation between aqueous concentration and adsorbed concentration is not changing, right? But what if I have another solute in the system, say carbonate, as I already mentioned, which can interact with uranium? So what we see when we put carbonate into the system, what happens here, as you can see, I am getting 3 different isotherms, right? And then you have a 3.3 grams per liter, that is G, right? That's the lowest amount absorbed. Then I increase the soil solution ratio to 33.3. I have another isotherm. I essentially kind of multiply it by 10, right? And then I essentially go for a higher solid solution ratio, 333 grams per liter. I have a totally different isotherm. So why this happens essentially is, of course, it's a monosolid system anymore. You have carbonate. Carbonate can form aqueous complexes. It will stop uranium from absorbing onto iron oxides. That is a competition that is going on between uranium and carbonate and the surface. That is essentially provided. So whether uranium wants to stay with the carbonate in the solution, or whether it has a more propensity to absorb onto iron oxide and remain on the solid. So that competition process essentially will decide what type of isotherm you're going to get. And me performing the experiment at multiple solid solution ratios is not going to give me the same isotherm. Of course, its isotherm is supposed to be unique, but I am not going to get a unique isotherm in this case. But imagine how many, the natural groundwater system, it is not just uranium and carbonate. We have tons of other things as well. You have phosphate, you have dissolved organic matter, you have n number of other things that are present. So really what we have in a very simplified scenario in the lab is not really going to work unless otherwise we capture the chemistry of the system, right? So that is what essentially your geochemical models are essentially showing. And this geochemical modeling tool is able to decipher the process, right? And is essentially highlighting the implications of going by the traditional approach. The need for geochemical software tool is essentially highlighted here. So moving on, so what is causing this? Different types of different isotherms when I change the solid to solution ratio. If I ignore the chemistry, I'm going to miss out on this process. But the incorporation of the chemistry is actually telling me that one is not going to have the same isotherm if one is changing the solid to solution ratio in a multi-solute systems. And of course, we explored what is causing this. If you look at the various complex reactions, that reaction sets, I think these are the reactions that are part of the model that are incorporated. This uranium can form aqueous complexation reactions. You please recall my introductory slide, I was talking about aqueous complexation. Uranium essentially is in the form of uranyl ions, UO2 plus, and it can form a series of hydroxides with different distribution coefficients. And uranium, if carbonate is present, can form uranium carbonate, uranyl carbonate as well, right? So one need to incorporate these uranium carbonate reactions as well. Okay, of course, you have carbonate reactions as well, carbonate from carbonic acid. These are the sets of reactions, and dissociation of water is incorporated. And these are the surface reactions, the absorption reactions or surface complexation reactions are shown here. So as I said, iron oxides is the surface, FeWOH. I think here we assume iron oxide is of two different types. This is a model that is taken from a well-established model, and also kind of used by Barnett in 2002 as well. It's a well-regarded model where iron oxides having oxygen lying on the iron at two different sites, say edge site and the equatorial sites. So these are classified into strong site and weak site, and uranium can actually attach to the edge sharing oxide or a corner sharing oxygen at two different equilibrium constants will be actually deciding that. So these are essentially, these equations are telling us what is the relationship between iron oxide and the uranium, in what way it is going to absorb, what is the ratio that's going to be maintained. And this is one of the important equations where you can see uranium doesn't absorb just like uranyl onto iron oxide. Uranium carbonate, if it is present, that can absorb as a whole into the iron oxide surface as well, right? So essentially, bringing this chemistry would help in essentially predicting what if the system becomes multi-solute. So that is what, or which is more closer to the realistic scenarios than the traditional, the distribution coefficient type approaches like Langmuir or Fromm-Lake or the KD approaches. So other reactions are being highlighted here, where just carbonate can itself just absorb onto the iron oxide without uranium as well. So there's a multitude of scenarios in which either carbonate can absorb onto iron oxide, carbonate can combine with uranium and absorb on iron oxide, or uranium just as such without carbonate can absorb onto iron oxide. So the competition between them essentially are captured through the equilibrium constants or the stability constants, the values that are given here. So the model essentially, the geochemical model essentially takes these into account, and based on iterative procedure that is going to solve those set of reactions and is going to tell what is the dominant reaction, accounting for the competitiveness between aqueous complexation and surface complexes in the presence of carbonate and in absence of carbonate, whether what amount of uranium is going to attach to iron oxide. So that is essentially you derive an isotherm from there, and that will be used for calculating the transport of the contaminant and to predict it for the future scenarios. Moving on, so as I already mentioned, I think so the reason why we see knowing the background now, so what is causing the differences in the uranium solid solution ratio effect, we change the amount of carbonate that is present, which is going to happen in the real scenarios, right? And then if we have a limestone aquifer, right, so carbonate concentration is going to change over time as infiltration happens at different times. So if you increase the concentration of carbonate, you are having a decreased absorption of uranium. So which essentially tells, if you're having a decreased absorption, essentially means you are going to have increased amount of uranium that is present in the groundwater, right? So absorption is less, your groundwater concentration of uranium is going to be more. All right, so essentially the carbonate essentially pushes the uranium into aqueous phase. So higher the amount of carbonate, or in bulk words alkalinity we can call, higher the amount of alkalinity, you are going to have higher the amount of uranium in the groundwater systems. So alkalinity has a direct correlation that emanates out of this geochemical model. Clear? If before we move on, if there are any questions in this part, I'll be glad to answer. We'll be moving on to fluoride contamination scenarios. or are there any questions from the audience? Okay. So moving on, in that case, yeah, I think I'll move on to the fluoride study. I think this study was done through the Indo-UK project of the DST and EBSCR funded the UK part. And this is essentially, we are looking at the fluoride contamination in Rajasthan. I think it is the arid and semi-arid regions essentially contain, in India, essentially contain quite some fluoride in the groundwater. And so it's of geogenic origin as well. And the incidences of fluorosis and scalatosis are quite prevalent in Rajasthan, and quite some activities from the Ministry of Jal Shakti has been there. Even this Indo-UK project is essentially had the Jal Shakti component of the push essentially. So we want to look at how the MAR structures, managed aquifer recharge structures, are important in addressing the fluoride contamination scenarios in the Rajasthan, affected regions of Rajasthan. Okay, so here in this study, we have collected soil from 2 different sites. One of that site is located in Jaipur district, and another one is located in Bharatpur district. The one that is located in Jaipur district is called, is in the place called Laporia village, and they have a unique water harvesting structure that is called as chaukas. So chaukas are just like a carom board, right? So the literal translation of chauka is 4 sides. So essentially they have bunds, small bunds that are essentially constructed and in a slopey terrain, and where the water is very, if at all rain, and Rajasthan being an arid region, whenever rainfall happens, they use these chaukas to collect water and essentially retain water in one particular place. So they essentially use these as water harvesting structures for allowing for percolation to happen at for longer duration. So the idea here is in Laporia, in the chaukas, in the chauka structures, since infiltration is happening largely in this village, whether this infiltration of rainfall is that going to cause any additional fluoride release into the groundwater systems, right? So that is essentially what we are looking at. And in the village of Bayana, it is essentially sandy type terrain. It's alluvial essentially region where there is a water body, a stream, small stream that is passing by. So essentially we picked an alluvial terrain for Bayana village where fluoride presence is being noticed. Primarily this study, this presentation will focus on the Laporia scenario. Okay, so what we did here is we collected soils from different depths, essentially, and we are looking for fluoride at from the surface and to the multiple layers in the subsurface, right? So that is essentially the idea, and how much of release is happening from which layer we are essentially looking at, and to come up with a geochemical model to explain the relationship between soil and the aqueous equilibrium scenarios in the water essentially. So what is that relationship? How we are going to capture it so that we can address what is essentially causing the release and how much of the release is happening, so we can quantify the release and it can be predicted spatially and temporally by incorporating the changing geochemical conditions over space and time. So moving on, so here is the kinetics that we did. There are, as I mentioned, we collected soil from at multiple depths. Say L1 to L6 represent soils obtained from different depths. L1 is from essentially the ground surface, we can say 30 centimeter from the 1 feet from the ground surface, and essentially every 30 centimeter we moved on as we collected soil, and it went till 1.8 meters from the ground surface. So essentially we have 6 layers, and you can see there's a clear distinction between the surface layers L1 to L3 and beyond L3, right? So what we observe is the fluoride that is essentially leaching out in these are batch studies, of course. The fluoride that is leaching out over time, right, is essentially we see more amount of fluoride that is coming out from the bottom layers when compared to the top layers, right? So there is a clear distinction. So what is causing that? Essentially, whether the geochemical model is going to give some insights into that is what we are actually attempting. So as already mentioned, higher release of fluoride from lower lower soil layers than the upper layers. And we have to keep in mind that the upper layer essentially is the root zone, right? So is there any interaction of soil water and the root zone that is essentially causing this change? That is essentially something to ponder about, as I think about. So, and one other thing we noticed was it's a highly dependent on pH. So I'll present the, as you can see on the right hand side, we picked the layer 2 and layer 6, one from the top layer, another from the bottom layer, and we performed. What if we change the pH of the system and how the pH is going to affect the fluoride release? As you can see, at higher pHs, essentially beyond 7, you see a higher amount of fluoride release, right? So pH is one of the factors that would affect, and which, if you're going by the traditional approach, we will be missing out on it. So one important aspect of the geochemical tool is we have to, this essentially aids in incorporation of pH changes that can happen to the groundwater. I think we collect groundwater at different time points, like pre-monsoon, during monsoon, or post-monsoon, right? And then or winter or whatever. So in those kind of scenarios, how the, of course, there will be changes in pH primarily, right? And so the bulk parameter. So in that case, how the release of the fluoride is going to be affected? It's, as you can see, it is very obvious. When the pH is dips towards the alkaline range, you are going to see a more release of fluoride, right? And one way to remediate the fluoride contamination is we produce the pH of the system. Essentially, it go towards the acidic range. Essentially, fluoride can get immobilized or less release can happen, right? So we do see that for layer 2 and layer 6. There's a common trend that is going on. So one other important aspect we could find, and these are the model predictions, experimental and the model results, surface complexation model results. One other thing, the surface complexation model that used was, we need to capture the reaction between aluminum that is essentially leaching out along with the water that is present in the groundwater. Unless otherwise we capture the presence of aluminum, which can form aluminum fluoride, and fluoride attaches as aluminum fluoride surface complex, we will not be able to capture this experimental result, right? So essentially, these are the major aspects of this geochemical model that emanated out of this particular study. So this is a reasonable prediction. For natural scenarios, you have an RMSE of 11.7%, around 10% is pretty much okay. So moving on, I think, as I already mentioned, we did for 2 different sites, La Puria and Bayana. I think Bayana also had the same type of scenarios where you have the lower layer, layer 2, have lower amount of fluoride, and the deeper layers having high amount of fluoride. And it's essentially the pH, higher the pH, higher the alkalinity, essentially is driving the fluoride contamination more. So these are essentially captured using the geochemical models. So as I already mentioned, what is this geochemical model reactions? As I already shown for uranium, these are SOH is a generic surface site. Unlike uranium scenarios where you have an iron oxide that is absorbing, since we are dealing with natural systems, we have a generic site that is labeled as S. Okay, it can be iron oxide, it can be aluminum oxide, it can be manganese, right? So it can be anything. So that's marked as being a surface. And the hydroxide that are sitting there on the surface can protonate or deprotonate in the first 2 reactions. And fluoride, if it is present, it can essentially form surface, can attach to fluoride, forming SF. That is essentially your absorption happening here. And the last reaction, as you can see, aluminum can combine with fluoride and attach to the surface as SOAlF2 as well, right? So all these reactions have an equilibrium constants that are essentially going to decide upon what is going to absorb, how much it is going to absorb based on the log K values. Okay. And as already mentioned, there's a positive correlation of fluoride with increase in pH, indicating the changing geochemical conditions are vital to capture and predict fluoride mobilization. So finally, I think I would like to wrap with this message. I think this shows the need for the geochemical modeling tools or capture the reaction sets, which the traditional modeling approaches are never going to capture, right? So one cannot do tens or hundreds of isotherms at varying geochemical conditions. It's hard to do that. Whereas these tools, geochemical software tools, essentially provides a platform where the dynamic chemical conditions or dynamic changes in chemistry of the groundwater are essentially captured through these geochemical modeling tools, which would aid in capturing realistic scenario that is happening in the subsurface environment. Okay, so I have shown only the batch scenarios. Of course, these batch systems, I think, is in the end we would like to include this in the transport model, and the transport model will incorporate all these equilibrium reactions, and essentially can be useful to predict the contamination scenarios both spatially and temporally. So those are done through modeling tools like visual ModFlow or groundwater modeling systems, and one can also code it and actually just solve the equations using simulation tools as well. So with that note, I would like to wrap this presentation, and I would like to acknowledge the patrons, coordinators of SPM Nivus, and Ishfaq ji. Essentially, I think he is the one that gave this opportunity and essentially made me part of this program. A special thanks to him, and the Jal Jeevan Mission. I think it is very good initiative, and I look forward to see this seminar series take off in a big way. And the work that is being presented here is supported by DST, SCRB, and Department of one of the theoretical studies that I presented was done during my PhD times. That's supported by Department of Energy, USA. And some of the work are done by the fluoride studies done by my research scholar. And finally, I thank my the Home Institute, IT Roper, for essentially giving me the platform to work and do good research. So with that note, I would like to end with this quote. A famous quote by a Senegalese conservationist, Baba Diouf. In the end, we will conserve only what we love. We will love only what we understand, and we will understand what we are taught. And I hope this seminar series is essentially aimed at essentially conservation and protection of the environment, and provides a platform to disseminate things that we do for our Mother Earth, essentially. So thanks a lot for your attention, and I'll be glad to take up for your questions. Yeah.
Good evening, sir. I am Dr.
Yes.
Bindupol from Kerala Groundwater Department.
Yes, ma'am. Yeah, please go ahead.
Here it is the uranium contamination. And the second one is here we are facing fluoride contamination in Palakkad as well as in Alappuzha district. In Palakkad, we are recommending rainwater harvesting, mainly for groundwater. So whether this rainwater harvesting directly to these open wells affect the fluoride increase in water level, water samples. That I want to know, sir, because we are recommending catch the rain program as the part.
Okay. So what is the second question, madam?
Fluoride contamination related to groundwater, this rainwater harvest. We are recommending it, but in my sir.
Okay, ma'am. So you said two questions. The fluoride question is the only one I can. What is the other question?
Other one is any uranium is detected in Kerala coast or Kerala, because we don't have this. We are not doing such a program.
So I'll answer the fluoride question first. I think fluoride, that's the common cliched saying in the environment domain, especially water quality, is the solution to pollution is dilution. Okay, so with rainwater harvesting, what we do is dilution of the pollution scenario. Yes, it would help. In common sense approach, yes, we expect the pollution to get diluted when infiltration happens largely, right? So that is what we are doing, or essentially we do the rainwater harvesting or recharge that happens, right? But the Indo-UK project that I presented here, it's essentially addressing the problem in the other. There is a spin to that particular the common parlance phrase. The solution to pollution is not always dilution. That is rationale for taking up this Indo-UK project. So what essentially happens during this in rainwater harvesting, in the case of fluoride I'm talking about, let me just highlight that. So in the case of fluoride, it is not just fluoride that is getting diluted. As I already mentioned, we are not really concerned, or we will be very limited in scope. We are looking at only that particular contaminant. We have to look at what are the other chemical constituents that is going to affect that particular contaminant, right? So uranium, it is not just uranium we are looking at, it should be uranium and carbonate or uranium phosphate, which can change its absorption capacity or mobilization capacity. So in the case of fluoride, so there is this dissolved organic matter, the issue of dissolved organic matter. The presence of dissolved organic matter essentially can affect the fluoride mobilization as well, right? So as you are doing the rainwater harvesting, if that leads to more amount of dissolved organic matter reaching the water table, you may not expect a lower fluoride scenario. The DOM may result in enhanced fluoride release.
Yes, that is
All
we know here. That's why.
Right, exactly. Right. So one need to look at the problem in a holistic scenario, right? And then the Indo-UK project is that is what the one of the major aspects that we want to address is what is the effect of DOM when this. We essentially go by this common sense approach. Let us dilute the thing with more kind of infiltration or recharge, but it may lead to higher amount of pollution as well in the case of fluoride. So I would probably suggest to look into the broader picture of the problem rather than limiting just to fluoride.
Okay.
So recharge may help in probably reducing other contamination, but in the case of fluoride, DOM can play a role.
Okay. Okay. That also we will.
Yeah. Okay. Okay. And your second question on this uranium in Kerala, if I remember, I think the Kovalam, the coast of Kerala is known for its thorium levels, right? So natural thorium occurs there. So rather than uranium, I would be suspecting thorium presence. And thorium can lead to uranium as well. I think in its one has to look at the decay chain of thorium. So see if I'm not aware currently. But one thing that is happening because of this AERB thing is the Atomic Energy Board has essentially given quite some projects all over India, looking for asking the research organizations to look into uranium levels in their groundwater. So I do know of some studies done in Kerala looking at the uranium levels. I'm not sure how much of contamination is present. I'm pretty sure it will be less than Punjab. So Punjab may we see quite some uranium contamination, and the reasons are different. But in the case of Kerala, I think I don't know the reasons that would cause the uranium. On top of my head, I could not recall. But as I already mentioned, the CGWB report of 2020, if I remember right, essentially tells the uranium levels in 18 states of India are above the ERB norms.
Okay.
So that is it actually. So Kerala may be one of that 18. Yeah.
सर नमस्कार.
Yes.
Thank you, sir.
सर मैं अमित.
Yeah, thank you.
सर आवाज आ रही है मेरी?
Yes, sir. Please go ahead.
सर अमित सिंह, मैं चीफ केमिस्ट PhD हरियाणा.
Okay. Yes, sir.
हरियाणा में भी रिपोर्टिंग हो रही है यूरेनियम की बाय सेंट्रल ग्राउंड वाटर बोर्ड, और अभी भी एक नया अलर्ट जारी किया है.
Okay.
सर मेरा एक क्वेश्चन ये था कि मैं जब स्टडी कर रहा था यूरेनियम की लिमिट्स के बारे में डिफरेंट कंट्रीज की,
Right.
तो किसी कंट्रीज में ये 1700 ppb दिखा रहा है और किसी में 30 ppb दिखा रहा है. तो क्या वो 1700 ppb हार्मफुल नहीं है और हमारे यहाँ 30 ppb हार्मफुल है?
17 is what? Can you translate that in English?
1700.
Okay. Sorry, yeah, my English, Hindi to English is not that good, especially numerics. So
And
English,
in Japan,
okay.
it's 2 ppb only.
All right, I think we do see quite some high levels in many pockets. I think if you go by the WHO or ARB norms, anything above 30 micrograms per liter, 30 ppb is for drinking purpose. One cannot use it, going by the drinking water standard, right? And then the AERB relaxed it to 60 micrograms per liter, 60 ppb. Anything above 60 is not supposed to be used for drinking. That's as straightforward, as straight as it is. So 1700, 1800 and all is no way I think one can use it. Yeah.
तो सर क्या वो वहाँ पे harmful नहीं है? It is not harmful for them.
It is harmful. I think that one should adhere to the limits. The limits are based on the hazardous nature of the contaminant, right? One need to adhere to the limits. It is harmful. If you want a little more technical answer, I think I didn't actually put it on the slide, but the toxicity of the contaminant depends on what is the type of species that it is, right? So as I already mentioned, uranium when coupled with carbonate, it would be harmful to the health. But uranium, when it is along with, say, phosphate or just lies as uranyl ion, UO2 plus, it can be released by the body directly. It will not be affecting the human health. So the speciation has the correlation to the human health as well, which we don't really look into. So to make the answer simple, I would say one need to adhere to the drinking water limit, forget about the speciation and all those things. So anything above the 10500 2012, right? So that is the water quality standards given by the BAS for drinking water. If that is exceeded, one cannot use it. Yeah. For drinking, of course, yeah. So any other queries?
Dr. Sanjeev Agarwal. Dr.
Yes,
Sanjeev
sir.
Agarwal is there. He's raising his hand.
Kindly
Yes,
share.
sir.
Yes, sir.
Okay.
Am I audible, sir?
Yes. Yeah, please go ahead. Yeah.
Okay, sir. Thank you very much, sir. Very nice presentation we have seen.
Yeah, thank you.
And what we observed that you have focused only on uranium and fluoride.
Okay,
But
so
in
what
other parts of the country,
Right.
there is a huge problem of arsenic in West Bengal and other
Right.
places. In
Right.
Odisha, also fluoride. In many states, we observed that. So, this is there any kind of a study modeling has been done for arsenic
Yeah,
in
sure.
West Bengal or for,
We have looked at the arsenic. Yes.
nitrate?
Yes, sir.
Yeah, please.
We have looked at arsenic issue as well, especially in Punjab also has arsenic issue, especially the Amritsar region, right? Northern Punjab essentially has the arsenic issue, and we recently published an arsenic study as well. If you can connect me, share your email ID. I think my email ID is Vijan and my name at iitrpr.ac.in. If you can just send a mail, I can just share that article as well.
Okay.
So yeah, but
Okay,
for time, I limited this presentation to uranium and fluoride. But arsenic I think we have attempted a study with soils of Punjab, and we have essentially have a model, geochemical model that can be used for arsenic absorption prediction as well. Yeah. So yes, of course, arsenic is a major issue, not just in the eastern part of India, which gets highlighted a lot, the West Bengal and the Bangladesh region, but it is there in Punjab and other regions as well. So yeah, it is. Yeah, we have worked on it, and I couldn't put it in the presentation, but for time. Yeah.
In the chat box, sir, I will share my email ID.
Okay.
Or can I get your email ID so that I can communicate to you?
Yes, sir. My email I just mentioned, right? Vijayanand. My name Vijayanand
Okay, here.
at
presentation.
iitrpr.ac.in. Yeah. No, in the presentation.
Okay, sir.
Yeah, you can go to IIT Roper website, civil department. I will be there. But anyways. All right.
Mr. Dr. Agarwal, you can contact us also to get email ID of Dr. Al Vijayanand. Dr.
Thank you,
Sanjeev
sir.
Agarwal, sir, you can do that.
Yeah,
also.
I will share.
Okay.
Yeah.
Okay, thank you very much. It's a brilliant presentation indeed. Anybody else who might be waiting to ask any question? If there is no raising hand, I have seen.
Yeah, good evening, sir. So this is
Yes,
Manju from I'm
Yes,
working
ma'am.
as a microbiologist in Department of Water Supply and Sanitation. I have one question that you recently just mentioned that uranium is present in different forms. Do you have some idea what is the status of the soil and in which form uranium is present in the Punjab soil?
So based on our work that we have done, I think carbonates can play a major role, right? And that is actually a work in progress. So yeah, I would probably say uranium carbonate can be one of the uranium in carbonate form, maybe the primary. And of course, it depends on the pH of the system as well. If we are looking at a scenario of 8.5 pH in Punjab waters, right? So groundwater in Punjab is essentially in the alkaline, close to alkaline region. So here the carbonate that itself tells uranium in the form of carbonate could be the dominant form that it would be present.
Okay. So
But I'm
as you
not
also
sure. I think one need to do much more studies. Like if you look at the speciation, one is supposed to do little studies like exaves and zanes that will essentially going to use neutron scattering or light scattering, X-ray scattering at the mineral water interface to get those information. But right now with this geochemical model, I would probably, on the pH scenario, the carbonate can play a vital role in uranium speciation.
where I can get the information about the geological data of the Punjab soil, especially if I talk about the Moga, Firozpur and Fazilka district.
CGWB report, madam. I think quite some things are documented in CGWB reports. Yeah.
Right,
I
right.
think that is
So I have
probably,
one more question. When uranium is reduced from its +4 oxidation state to +6, becomes highly mobilized. But it
oxidized,
is
right? Yeah.
Yeah, but it's often seen the case the uranium is found in one location within a village, but just a few meters away, there is no
Right.
uranium contamination found. What could be the possible reasons for that?
So one need to essentially look at the geology and the water quality in a broader sense that can give the solution, that can provide insights, right? It's more like a forensics. So one need not just look at uranium only, one need to look at the bulk water parameters, right? So individual water parameters, how that correlates
Yes,
to
of
the
course,
presence of the
every
contaminant,
parameter
right?
is correlated. Yes, of course, I got your point.
Now,
Just
okay.
wanted to say that when uranium switch from +4 to +6, it becomes mobilized. Then why it's happening that we are just boring a few meters away the same well and it is not uranium contaminated, and few meters away we are finding the uranium out of the permissible limit. What could be the possible reason? Sometimes it's unanswerable that why it's happening, because both the wells are from the same aquifers, have the same depth, but
Okay.
why the uranium is not moving just few meters away? And I got it that uranium is geogenic, but why these days in this contemporary era it's amplifying? The geogenic it's
No, the
present
one reason for
last.
amplification is we are probably looking at it for longer. We are looking at it more. Probably
Yes,
we
sir,
were
because
studying it less
we are
before.
doing
These
random
days we are
testing.
right. We are testing it
Yes.
for with the fluorimeter and all those things the ARB has put up. We are more the number of times we look at the problem apparently looks magnified. So
Yes, sir.
I don't know. Yeah, as I mentioned, but I don't have an exact answer to it. Why within few meters it changes? One need to look at it in a comprehensive way. I think probably you can tell me this. I am in Punjab only. I can have a look at it. I can probably
Yes,
look
sir.
into
I
that
belong
problem.
to
Yes.
Punjab
Yes.
itself. We are
Right.
from the Department of Water Supply and Sanitation. We have a
Okay.
great amenities of the laboratories. We used to have a uranium testing annually, but we are not able to locate the proper reasons. We are not focusing on the how and why. Though we are doing random testing, we have a lots of data
Okay. Yeah.
available, uranium, arsenic, and lots of heavy metals. We are
Right.
not reaching to the conclusion how we can
Right.
dilute and how we can get rid of this. We are not approaching
Oh,
to that.
remediation is one aspect, madam. I think understanding it helps in remediation. Remediation methods or tons of remediation methods are there. Once we have
Sir,
addressing the
this
problem is
both
different, but understanding the problem is different. That is at a different
yes,
level, right? So
yes,
yeah, my presentation is more of understand. I never talked about the remediation aspect of it. I am just looking at how to understand the problem in a better comprehensive way, right? So how the modeling tools can be used. So once we know what is causing the issue, then we can address it in a better way. So
right.
I'll be this problem of uranium in Punjab, we are looking at it. It is a work that is in progress in my lab as well, right? So we are working on it also. I have this early career research award from SERB, in which I kind of I had the proposal on uranium got funded, and that is a work in progress, and probably down the line we may have some answers to it.
Okay, thank you, sir.
Yeah.
Thank you for this talking.
Yeah, thank you.
I have not seen any more questions from any participants. No raise hand. Dr. Sanjeev Agarwal has already asked a question. Amit Kumar Singh ji has also clarified his doubts. Any more questions, please? or we'll close this session. It is indeed a very brilliant presentation, very informative.
Yeah, thank you so much.
So we are expecting to further more presentation from the faculties
Sure.
of Genopal.
Sure.
And now it's time, because it is almost 5:14. So we are going to close this session. So once again, a very warm congratulations to Dr. L. Vijayanand for his brilliant presentation. And I believe all the participants have learned a lot from him regarding the mechanism of contamination. It's for uranium and this fluoride is concerned. And thank you very much, the participants also, for their participation and asking different questions to Dr. Anand for clearing their doubts. With these few words, I want to close this session. Thank you once again. Thank you very much.
Yeah, thanks everyone for joining this seminar. And, thanks for attention. Yeah. Right.